So, welcome one and all. In this lecture, I will discuss types of random variable. Actually, this is the lecture number 3 in the series of random variable and probability distribution. Okay. Now, basically, we have two types of random variables. One is what we call discrete random variable, and another one it is what we call continuous random variable. Now, if a random variable, it takes the countable number of values, or a random variable, if its set of possible outcomes is countable, then we call that random variable discrete random variable. Okay. So if the values taken by or assumed by, taken by or assumed by the random variable r dot v dot random variable, if these are countable or are countable. Okay, if the values are taken by or assumed by the random variable r, so here it should be R. Okay. Then we say the random variable is a discrete random variable. Okay. And if the values taken by or assumed by the random variable, they are uncountable. They are uncountable, or when a random variable can takes on values on a continuous scale or in some range or interval. Basically, for example, if the random variable is having values, say, in the range from 10 to 12, in this range. Okay. Now, in this range, there are uncountable number of real numbers in this range or in this interval or continuous scale. There are uncountable number of real values or real numbers. Okay. So, if the random variable x, it is taking the values in this range, in such range, then we call it continuous random variable. Okay. Now, if you recall back, actually, in the previous two lectures, I have discussed these examples. Now, in all these examples, our random variable was discrete random variable. How it is a discrete random variable? Actually, in the very first example, our random variable x, it was actually the number of tails. Actually, we calculate. So, in this example, our random variable was x, which was actually number of tails. Actually, we calculated the probability distribution of the number of tails. Now, this number of tails was our x, the random variable, and x was having the values 0, 1, 2, 3, and 4. So this x, it was having. So now this x, its values are very well countable. This is my first value, second value, third value, fourth value, and fifth value. Means, means the values taken by this x, they are countable. Similarly, in this example, we calculated the probability distribution of number of red balls selected, and this number of red balls selected, it was our random variable, we denoted by x, and this x, it was having the values 0, 1, 2. Even here, this x, its values, they are countable. Means here there are only three values: first value, second value, and third value. Okay, and now. And similarly, in this, in the next example, so in this Bernoulli trial is in this example, Bernoulli trial is conducted until first success appears. Here, the number of trials for the first success. Okay, this was our random variable, and its values were actually x, 1, 2, 3, 4, and going on. Okay, although x here, the values of x are infinite. The values of x are infinite, but still they are countable. I can count because this is the first value, second value, third value, fourth value. Okay, although they are infinite, but still they are countable. And similarly, in this example, we calculated the probability distribution of number of failures required for the first success. Okay, or number of failures preceding the first success, preceding the first success. Okay, so here this the number of failures, it was our random variable x, and its values were 0, 1, 2, 3, and going on. Even here, the values of x, they are infinite. Okay, but still they are countable. First value, second value, third value, and going on. So all these examples I have discussed, very well discussed in the previous two lectures. If you are interested, please watch those lectures. Okay, but in all these examples, our random variable was taking countable number of values, whether the number of values were finite or infinite. Okay. Now, this is what we say a discrete random variable. And what is a continuous random variable? Now, actually, time is an example of continuous random variable. How? Suppose we are calculating the age of a person whose birth date, it is say it is 13th March 1980. Okay. Then today it is 19th of Jan 2025. Today it is this one. So what's the age? Actually, we are interested in the exact age of that person, the exact age of the person. Okay. And we are denoting by random variable x. Okay. Now this x, what is this exact age? Obviously, this exact age, it is lying in this interval 44 to 45. This is the most accurate answer for the exact age. Please mind, here we are calculating exact age. Why? If we simply say that the age is 44 years, this is 44 years, then it is not exact. So for 44 years further, it will be some months, say say 9 months. Okay. But still it is not exact. Actually, further, it will be some days, then some hours, minutes, seconds, nanoseconds, femtoseconds. Okay. So actually we can go on. We can't calculate, or we can't tell the exact age in this way. Okay, means we can't say that x is exactly equal to some c. We can't say that x is exactly equal to some c, or x is discretely equal to some constant c. Rather, the most accurate answer is that x lies in this interval. Okay. Now, it means that x is taking values in a continuous scale, or in some range or interval. So age, which is a measure of time, it is nothing but an example of continuous random variable. Similarly, height, which is a measure of length, it is also a continuous random variable. So, suppose the height of a person is, say, 5 feet 11 inches, it is 5 feet 11 inches. Okay. Then this will not be the exact height. Actually, once again, we are now we want to we want to calculate the exact height. We want to calculate the exact height of a certain person. So say it is 5 feet 11 inches, but this will not be exact height. Rather, it will be further some centimeters, millimeters, okay, nanometer, femtometer. So, what will be the most accurate answer? The most accurate answer, that the exact height, suppose I denote it by the random variable y, it will be that it lies between 5 to 6. Okay, yeah, range we may change. that y lies between 5 feet 11 inches to 6 feet. 5 feet 11 inches to 6 feet. Okay. So even here, we can't say that the height of the person, which we are exact height of the person, which we are denoting by random variable y, it is discretely or exactly equal to some constant c. We can't say this thing. Okay. So now time, height, okay, length, weight, and temperature. Okay, these are some examples of continuous random variable. Okay, but one remark here, suppose in a particular situation or in some question, it is mentioned that we have to measure the time only in integral values. We have to measure the time only in, say, integral hours, okay, integral values of hours or minutes, okay. So in that case, time will be nothing, it will become discrete random variable. Why? Because either we will have 0 hour, 1 hour, 2 hour, 3 hour, or 1 minute, 2 minute, 3 minute going on. Okay. So this is the concept of continuous random variable and discrete random variable. Actually, this behavior, which is basically discrete behavior and continuous behavior, it is possessed not only by random variables. Actually, it is possessed by almost every measurable physical quantity in this universe. This behavior of discrete nature, the behavior of discrete nature and continuous nature. Okay, it is not only exhibited by the random variable, but actually these two types of behaviors, they are exhibited by almost every measurable physical quantity in in this universe. Say we know actually light has two type of behavior. One is what we call particle nature. Okay, particle nature means the light is made up of photons. Okay, and there is another nature which is actually wave nature, the wave nature of the light. Okay, so the wave nature, actually it is the continuous nature of light, and particle nature or light is made up of photons. It is nothing but discrete nature. How? Because we can count the photons. Okay, we can count, it is the first photon, second photon, third photon. Okay, and there is another that is called wave nature. Actually, some phenomena of light, say photoelectric effect, they are explained by the particle nature of the light, and some phenomena, for example, diffraction, okay, they are explained by assuming that light has wave nature. And similarly, signals. Even signals are of two types. One type is digitized signal, digitized, okay, digitized signal, and the another type of signals are analog signals. Actually, digitized signals which are in zeros and ones means we can count zeros and ones. And what is the another type of signal, which is analog signal? Actually, analog signal is continuous signal. Okay, so just like almost every other measurable physical quantity in this universe, even the random variable has two type of nature or behavior. One is discrete and another one is continuous. So basically, we were discussing about probability distribution function in the first two lectures, or even in the previous questions, if you have observed, probability distribution function of some certain number of things. Okay, so this PDF now, the probability distribution function, Fn dot means function. It is of two types. One type, this is what we call probability mass function, PMF, probability mass function, and another one, probability density function. Okay. So if random variable is discrete, if the random variable is discrete, we call the probability distribution function as probability mass function. And if the random variable is continuous, if the random variable is continuous, we call the probability distribution function as probability density function. You can see here that these three properties, these we have already seen, I have already discussed in the previous two lectures, that this is what we call probability mass function, because our random variable is discrete. So we have already seen this fx, it is never negative for all values of x. Sum of the fx over the entire range of random variable, it is 1. And actually, this is the basic definition. This is the basic definition of PMF. So these three properties, they were very well discussed in the previous two lectures. Okay. So now, these three characteristics, actually these three, they are not different characteristics. Actually, they are parallel to these three characteristics. These three characteristics, okay, they are parallel or analogous to these three. Actually, here fx, it is our probability density function. The probability density function. Why? Because our random variable is continuous. So just like this case, just like the PMF, probability mass function, the probability density function, it is never negative for all values of x, which are real numbers. Now, uh, in case of discrete, we have summation of all values of x over entire range of x, the random variable. It was 1. But here we have integration of f. Okay, the integration of f over entire range of x, over entire range of random variable x, it will be 1. The reason for this, actually, this definite integration of some certain function fx, which is nothing but limit n tending to infinity summation fxi into delta xi, I1 to n. Actually, this relation, it is the relation between discrete case and continuous case. I repeat, this relation, what is this relation? It is nothing but the definite integration. The definite integration as a limit of, it is a limit of certain sum. Definite integration, it is limit of some certain finite sum. Okay, so this relation, it is nothing but the relation between continuous case and discrete case. Actually, for the basic classes, I'm not talking about the higher mathematics. I'm just talking about the very basic mathematics. Okay, to have the this integration of fx, to have the means fx is integrable. The fx is integrable. Usually, we say that fx is continuous. Fx should be continuous. Okay, so this side fx is means this side fx is continuous, but this side fx is discrete. How it is discrete? Because we have f at x1, then the value of f at x2, and then the value of f at x3, going on up to the final value of f at xn. Okay, so on this side, on the right hand side, okay, our f is having a discrete behavior or discrete nature, means f is taking value at x1 for I1, f is taking value at x2 for I2, going on up to xn. So on the right hand side, the function f is discrete, but on the left hand side, the function is continuous. So what is the crux of all this? The crux is simple, that if in case of discrete random variable, if in case of discrete random variable, we have summation. Okay, then in case of continuous random variable, we will have integration. Okay, so this is just a way to explain these things. But once again, this is we can't say that this is 100% mathematically correct. but yes, it works. Okay. So now, number three, this number three, it is the basic definition of our probability mass function. Okay, this I have discussed in previous lecture. And what is this one? It is nothing but the basic definition. This is the basic definition of probability density function. Actually, we know by now, so either x will be having some discrete value, x will be taking some discrete value, or x will be lying in some interval. Okay, means either x will be discrete or x will be continuous. But whatever the case, whether x is discrete or x is continuous, ultimately we are interested in finding the corresponding probability. Okay. Now, in this case, the probability, it will be directly given by fx. Okay, so this fx, it will have some values for every example. But for this one, means to find this probability that x lies in some range, for that, we have to integrate a certain function. We have to integrate a certain special function between a to b. Okay, and this certain function, this is what we define as probability density function. Okay, so for this case, this probability, it is directly given by fx. Okay, and this fx, it will have different values or formulae depending upon the our example. Okay, we have seen such things in the previous two lectures, but for this case, okay, means in order to find the probability that x lies in some range, we have to integrate a certain special function. We have to integrate a certain special function between a to b. And this certain special function, it is what we call the probability density function. So this is the basic definition of probability density function, and this is the basic definition of probability mass function. Okay. So I repeat that these three characteristics and these three characteristics, they are not different. Rather, these three, actually, they are analogous. They are parallel. Okay, these are parallel, means these three and these three, they are parallel to each other. Actually, the top three, they are the characteristics for probability mass function, and these three, they are the characteristics for the probability density function. Now, one thing here it is mentioned that such ordered pairs, x, fx, such ordered pairs, they are nothing what we call probability function, probability mass function, or probability distribution. Okay. But in the previous lectures, I was writing the probability distribution in the tabular form. Means x, it is having the value, say 0, 1, 2, 3. Okay, and here probability x is x, means here fx, which was nothing but probability x is x, so here f at 0, then f at 1, then f at 2, going on. Yeah, obviously, what is this? It is nothing but probability x takes the value 0, and what is this value? Probability x takes the value 1. Okay, going on. Now, I was discussing in this way, or telling in this way, that this type of tables, such type of tables, this is what we call the probability distribution. Why? Because these tables, they give us the distribution of the probability, how probability is distributed over various values of the random variable. But these tables we can write in some another form, that is 0 comma f0, means this ordered pair, then 1 comma f at 1, then 2 comma f at 2, means we can write these types of tables in the form of such ordered pairs. Okay, so you can see x is 0, then the value of f at 0. Then x is 1, the random variable x is 1, then the value of f at 1. Going on, you can see very well that x is 0, then f at 0. X is 1, then f at 1, and so on. So, whether we say our tables are nothing but probability distribution, okay, or we say such ordered pairs are our probability distribution, they are nothing but same, okay. And moreover, these are what we call ordered pairs. Ordered pairs, why we call them ordered pairs? Because in these pairs, the order of the elements, it is important. The order of the elements are important. So what is the first element? It is our the value of random variable. Okay, you can see. And what is the second element or second entry? This is nothing but the value of the PMF at the corresponding value of X. Okay, so ordered pairs. And actually there is a concept of unordered pairs also. That is unordered. Oh, sorry. It is unordered pairs. Actually, these sets which are having two elements, means suppose I am writing this one, AB. Okay, these curly brackets. So these are actually, this is nothing but a set. Actually, these are called doublets. The doublets which are having sets which are having two elements, they are unordered pairs. Why they are called unordered? Because here the order of the elements is not important. Means to say, this set, unordered set AB, and this set BA, actually they are same. They are same. Okay. And but in the case of this one, AB means these parentheses. Actually, for ordered pairs, we put parenthesis. Okay. So this parenthesis AB, it is not equal to the parenthesis BA. Okay, why? Because this is nothing but these parentheses, they are used for ordered pairs where the order of the elements is important. Okay. So here we have an example that a shipment of 20 similar laptop computers to a retail outlet contains three that are defective. Means out of 20, three are defective. Obviously, 17 will be non-defective. If a school makes a random purchase of two out of these 20, we have to find the probability distribution for the number of defectives. Okay. So once again, we have been asked that we have to find the probability distribution for some certain number of things. We have to find probability distribution for some certain number of things. So this certain number of things, it will be my random variable. So here X is the number of defective laptops. Okay, defective laptops out of two laptops selected, out of two laptops selected. Okay. Why so? Actually, we can comment that a particular laptop is it is defective or non-defective only if we have selected them. Okay, means what about those laptops which have not been selected? Okay, we can't comment on those unselected laptops, that which one is defective or which one is not defective. In other words, we can tell how many laptops are defective only if we have selected them. Okay, if we have not selected any laptop, we can't comment that out of these unselected laptops, these many may be defective, or many laptops will be non-defective. So here, what values this X can have? So it can have either value 0 or 1 and maximum 2. Okay, means out of these two laptops which are selected, either there is 0 defective. Okay, and if there is 0 defective, then how many non-defective will be there? Both the two will be non-defective. Or out of these two laptops selected, there is one laptop which is defective. So if one is defective, then obviously the second one will be non-defective. Or out of these two laptops selected, both the laptops they are defective. Okay. Then probability x is x. Okay, which generally we denote by fx. Okay. So now here, this value, it is nothing but, it will be zero defective. So 3C0. Okay, I'm writing here that probability X is 0. This is 3C0 into 17C2 divided by 20C2. Why? Because we are selecting zero defective. We are selecting zero defective. Out of total, how many defective? That are three. Okay, suppose we have D1, D2, D3. Okay, so these are the three defective laptops, and we have to select zero defective out of three. In how many we can do so? We can do so in one way. What is that one way? This is nothing but 3C0. Okay, and what is that one way of selecting zero defective out of these three defective? That way is select nothing. Select nothing out of these three. And obviously, if the zero number of laptops they are defective out of these two, okay, the two selected, then obviously both the two will be non-defective. And we are selecting two non-defective out of total 17 non-defective laptops. So the numerator is having the favorable number of outcomes and denominator is having the total number of outcomes or total number of selections which are possible. Okay, basically we have L1, L2 going on up to L20. We have 20 laptops. So out of these 20 laptops, we are selecting two. So these two, they can be L1, L2, L1, L3, L5, L9, or L10, L20. So how many such combinations are possible? There are 20 C2. Okay. Similarly, what will be the value of probability X equal to 1? Okay. So here, the probability that X takes the value 1, okay, which is nothing but f at 1. So this will be 3C1 into 17C1 divided by 20C2. And probability that X is 2. Okay. So this will be nothing but 3C2 into 17C0 divided by 20C2. Okay. So further, yes. If such question is an exam, then we should write simplify these values. So this is nothing but 3 and this is nothing but 17. And now 20C2, it is nothing but 20 factorial divided by 2 factorial into 18 factorial. Now this 20 factorial, it is 20 into 19 into 18 factorial. So 18 factorial gets cancelled. So 2 factorial cancels here. So 10 into 19, that gives us 190. So such simplifications must be done in the exam to score the better marks. Okay. So here, actually, there is once again, there is a shipment of 20 similar laptops to a retail outlet, sorry, having five are defective. And now four are being purchased and find the probability distribution for the number of non-defectives now. So now we are finding the probability distribution of some certain number of things. So this certain number of things, okay, so it will be my random variable, say I denote by y. So this y, okay. So what is this y? So here this y, it is nothing but the number of non-defective. Please mind the number of non-defective laptops. Okay, non-defective laptops among among the four laptops selected. Among the four laptops selected. Okay. And why this can have the values either 0 or 1 or 2, 3, and at max 4. Okay. And now probability y is y. So here it is probability y is 0. Probability y takes the value 1 going on. So probability y takes the value 0. It is nothing but actually 15C0 into 5C4 divided by 20C4. Why? Because we are selecting zero non-defective. We are selecting zero non-defective. Out of total, how many non-defective? There are 15. Please mind, there is a scope of mistake here. Here we are finding the probability distribution for number of non-defectives. So total number of ways of selecting zero non-defective out of total 15. It is 15C0. Okay. So zero laptop is non-defective, means all the four they are defective. And the four defectives coming out of how many total non-defectives? Five. Okay, so selecting the four defective out of total five, it can be done in 5C4 number of ways. Okay, and obviously this is our total number of ways or exhaustive total number of ways or exhaustive number of ways of selecting four laptops out of total 20. Okay, similarly, what will be this probability y equal to 1? So this probability y equal to 1, that will be nothing but 15C1 into 5C3 here and divide by 20C4 once again. Okay. And if it is probability y equal to 2 here, then 15C2 into 5C2. Okay. Divide by this, and further you can solve the remaining. Okay. So once again, whenever we have to find the probability distribution of some certain number of things, that certain number of things should become our random variable. Then we must check what type of values this random variable can have, and corresponding to those values of the random variable, we have to calculate the corresponding probability. Okay. But whatever examples I have discussed so far, even in this one, in this lecture, or even in the previous, one can very well see that our probability mass function, whether I was denoting it by fx, f at x, okay, which was nothing but probability that x takes the value x. So this, it was never negative for all values of x, for any or for all values of x. And one more, that summation of fx over entire range, whatever the range. Okay. So this range of the random variable, it varies from question to question. Okay. In this example, the range of the random variable, it is 0 to 4. Okay. So the sum of all probabilities over entire range of the random variable is okay. So one remark here, I have mentioned that the probability distribution function, it is called probability mass function if our random variable is discrete, and this is called probability density function if our random variable is continuous. There is a certain logic why such a nomenclature is given. Actually, mass, it can be treated as mass can be treated as a discrete entity, whereas density it is a continuous entity. Actually, in physics, there is a concept of center of mass. There is a concept of center of mass. Actually, with the help of this concept, center of mass, we can pinpoint discretely. Suppose I have a body, say I am having this type of body, some symmetrical. Okay, so this type of body is there. So suppose actually the center of mass is at this point. So I can pinpoint discretely. I can pinpoint discretely that the whole mass of the body, it is situated at this point. Okay, with the help of this concept of center of mass, I can pinpoint discretely that the whole mass of the body, it is situated at this point. Okay. And one more logic, Actually, just like there is a particle of light, there is a particle of light which we call photon. There is a particle of mass also, which is known as Higgs bosons. Okay, so if someone is interested in physics, then he must be having the knowledge of. He may be having the knowledge of this Higgs bosons, which is also called God's particle. Okay, so this Higgs bosons or God's particle, they are the particle of the mass. Means these are the particles which are responsible for the mass of anything in this universe. Okay, so that's why mass it can be treated as a discrete entity, whereas density. Okay, density is a continuous entity. How? Because just like mass of a body, we can't say just like mass of a body we can't say that the whole density of the body, it is situated at a particular point. We can't say. Okay. I repeat, we can't say that whole density of a body, it is situated at a single point, just like mass of the body. Why so? Because density is a continuous entity, means density is, it is spreaded throughout the body. Density of a body, it is spreaded throughout the body, means it is a continuous entity. So this is one possible reasoning, okay, in order to understand that why probability distribution function, it is known as probability mass function if our random variable is discrete, and why this probability distribution function, it is known as probability density function if our random variable is continuous. So here we have an example. Suppose that error in the reaction temperature in degrees centigrade for a certain controlled lab experiment. It is a continuous random variable whose density function is given by this expression. Okay. So I have already mentioned that temperature, time, length, and weight, these are some examples of continuous random variable. Okay, so here we have to verify that this fx is a density. This is actually a density function. Okay, now this part A, it may be asked in this way also. I repeat that this part A, that verify that fx is actually a density function. It may be asked in this way also, that for what value of k, for what value of k the following function will be a valid probability density function, or for what value of k the following function will serve as a probability density function. Okay, so for that, basically whether this one or this one, for this, we will apply the property, use the property that integration of this PDF over the entire range of the random variable, it must be 1. Now, here range is given to be between -1 and 2. So actually, we can directly write that between -1 to 2, this integration of fx, it must be 1. We can directly write, okay? Or we can do in this way that from minus infinity to -1, fx dx, okay? Then plus -1 to 2, okay? Just wait. Yes. So between -1 to 2, fx dx, and plus 2 to infinity, fx dx. Okay, this must be 1. So here, minus infinity to -1, -1 to 2, and 2 to infinity. So what is the total range? Minus infinity to infinity. Now, between -1 to -1, what is the value of this fx? It is 0. Okay. Between 2 to infinity, what is the value of fx? 0. And in this range, what is the value? Actually, the value is given by x square by 3 between -1 to 2. Okay. So since here fx is 0, so that's why the value of this integral, this definite integral, will be 0. And even here, the value of this definite integral, it will be 0 because even in this range, the value of fx is 0. Okay. So basically, we need integration of x square by 3 between -1 to 2. It must come out to be 1. So that is not a typical job to check. So basically it is 1 by 3. So integration of x square, it will be 2 plus 1 divided by 2 plus 1 between -1 to 2. Okay. And this should be 1. And now basically I am applying the formula. Okay. The basic formula. And now we have 1 by 3. Okay. Uh, it will be, so this 3 is here. So I am having x cube here between -1 to 2. Okay. And now it is 1 by 9. Okay. Actually, this 2 plus 1, it is here. And now 2 cube. Okay. Because x is 2. X is 2. Put upper limit minus, put lower limit. X is -1. X is -1. Okay. Even here, cube. And this must be 1. And now here it is 2 cube. So 1 by 9. So this is 8. 8 minus 1. And is it actually equal to 1? Yes. Because what is this thing? 9. 9 divided by 9 is equal to 1. So this proves that the given fx, it is actually a valid density function. So now, if this same question, it is asked in this way, so integration of kx square between -1 to 2. So this must be 1. So k is constant, and so it is x cube by 3 once again between -1 to 2. It must be 1. Okay. So integration of x square, it is nothing but x cube by 3. And now here k by 3, and put x2, put upper limit. Okay. Minus, put x equal to -1. So -1 cube, it must be 1. Okay. So from here, it is k by 3. And what is this thing? 8 minus -1. It must be 1. So from here, it will be 3k. That will be 1. Okay. Because this is 9. 9 divided by 3 is 3. Okay. So from here, what should be k? K must be 1 by 3. Okay. Means for k equal to 1 by 3, for k equal to 1 by 3, the given fx, it will become a valid PDF, probability density function, or it can serve as a probability density function. And obviously, this k equal to 1 by 3, this is our expected value. Somewhere we already know that this k, it should come out to be 1 by 3. Why? Because if you have observed in the first, so if someone has already observed in the first statement, here fx is given in this form, x square by 3. If x is in this range, 0 elsewhere. Okay. So here fx is x square by 3. So I have written in the form kx square. I have written in the form kx square. So what is k here? Obviously 1 by 3. Okay. So this fact was already, in a certain sense, it was already known to us. But here, a question may be asked in this form also. Now, for this second part, we have to find this probability that x is between 0 to 1. In a certain sense, we have to find the probability that the error in the reaction temperature, the probability that, okay, I write here. Actually, here what x represents, it represents error in the reaction temperature in degree centigrade. I repeat here our random variable x, it represents error in the reaction temperature in degree centigrade. Okay. Actually, one remark here, whenever there are such problems, we can call them word problems. So in such problems, we must have the knowledge, or we must be able to identify that what our random variable represents. I repeat, questions like these, we must be able to identify that what our random variable represents. If we can identify that what the random variable represents, then the question will be easy. Otherwise, it will become tough. Okay. So here we need probability that X lies in this range. So basically this is probability that the error in the temperature reaction, the error in the temperature reaction, okay, in degree centigrade. Obviously in degree centigrade it is between 0 and 1. Okay, so this question, it may be asked in this way, that find the probability that the error in the temperature reaction. I repeat, this part B, it may be asked in this way, that find the probability that the error in the reaction temperature, it lies in the range 0 to 1. Okay. So for that, obviously, I have to indicate a certain special function in the range 0 to 1. Okay. And what will be this certain special function? It will be nothing but our probability density function. Now, what is this probability density function in the given range? It is nothing but x square by 3. It is x square by 3. Okay, because it is mentioned that this fx, it is nothing but x square by 3 in the range between -1 to 2. It is, okay, wait, please. Yes, okay. So in this range, fx is nothing but x square by 3. And obviously, 0 to 1, x 0 to 1, it lies in this range. So that's why our fx is nothing but x square by 3. So now further it is nothing but 1 by 3 and x cube by 3 between 0 to 1. So this is 1 by 9. And here it is 1 cube minus 0 cube, which is nothing but 1 by 9. So this 1 by 9, it is the probability that the error in the reaction temperature reaction is between 0 and 1. Okay. So here we have to find the value of C, so that this given function, it can serve as a probability distribution function. We may call it probability distribution function or probability mass function. Okay, why? Because our random variable is discrete here. Okay, so this question, it may also be asked that find that value of C, so that the following function fx, it can become a valid probability mass function. I repeat, this question, it may be asked that find the value of C, so that the given function, it can become a valid probability mass function. So basically we are going to apply this property that x0 to 2 means sum of the values of fx over entire range, it must be 1. And here, this symbol, which is nothing but this, actually it is nothing but 2cx. And this 3 minus x, this symbol is nothing but 3c, 3 minus x. So we have c, then into 2c0 into 3c3 plus c 2c1 into 3c2, then c 2c2 into 3c1, that must be 1. So what is this value? Actually, this value is nothing but f at 0. You put x equal to 0 here. You put x equal to 0. Okay. And what is this value? It is nothing but f at 1. Means we put x equal to 1. Wherever x replaced by 1. And what is this value? It is nothing but f at 2. Okay. Now take c common. Okay, you can very well see, we can take C common. So now what is 2C0? It is nothing but 1. What is 3C3? It is 1. What is 2C1? Next, you can see it is 2. What is 3C2? It is nothing but 3. And what is 2C2? It is 1. Okay, and what is this 3C1? It is nothing but 3. That is 1. So from here, C. So it is 1 into 1 is 1 plus 6, 7, 7 plus 3, 10. C into 10 must be 1. This implies C must be 1 by 10. Okay. Means for this value of C, our given fx, for this value of C, our given fx, it will become a valid probability mass function. Okay. So now we will discuss cumulative distribution function. Okay, in short, it is known as CDF. Okay, so cumulative distribution function. So some authors they write them as CDF, and some authors they simply write them as DF only, distribution function. Okay, but I will be using CDF. Now, what is the meaning of cumulative here? This word cumulative, the meaning is start from the starting and come up to the present one. So I repeat, I write here, what is the meaning of this cumulative? This word cumulative. Okay, it is start from the starting, okay, or initial point, starting or initial point, and come come up to the present. Okay, come up to the present. So this is the meaning. Actually, if you recall back in your lower classes, you were having such type of frequency tables. So here I am having time. This is our data, time in minutes. This side is frequency. Okay, frequency of some certain number of things. And this side we have cumulative frequency. So here, what is the cumulative frequency itself? Now here, what is the cumulative frequency? Adding the previous two. Adding the previous two means the cumulative frequency up to this interval, okay, or this data. And what is the cumulative frequency up to this data? It is nothing but adding the previous three, means I need to calculate cumulative frequency up to this stage. Okay, so for that, what I am doing, I am adding the previous frequencies up to this stage. Similarly, I need the cumulative frequency up to this stage or this value of the data. I need the cumulative frequency up to the this stage or this value of the data. For that, what we will do, we will add the previous frequencies, start from the starting up to the present one. Okay. So this is nothing what we call cumulative frequency. So it is almost same as the given definition. Actually, the value of f at x, the value of f at x, it is nothing but probability that x takes all values less than equal to x. Means probability that x takes all values start from the starting, whatever the starting, okay, up to the present x. Okay, for example, say my random variable, it is taking the values, means the start value is say -3. I say the start value, the start value means the very first value. The start value of x is say -3. So what will be this f at x? It is nothing but probability x start taking value from -3 up to the present x. Furthermore, suppose I need the value of f at 4. I need the value of this function f at 4. Okay. So what is this function f? Actually, this function is nothing but our CDF, the cumulative distribution function. I need the value of this CDF at 4. I need the value of this CDF at 4. So what will be that? Nothing but probability that x takes all values but up to 4. Or it is probability that x starts taking value from -3. Why? Because my starting point or starting value of x is -3. And it will keep on taking the values up to 4. Okay, so this is the meaning of CDF. Okay, the value of f, the CDF at x. Probability that x takes, okay, all values up to the present x. And similarly, suppose it is f at 7. I need the value of CDF at 7. And say the starting value x is starting from, say, 0. X starts from 0. Yeah, x may be continuous. It may be discrete, whatever the case. So what will be f at 7? It is nothing but probability x takes all values up to 7, or probability that x takes values up to 7 but start from the starting point 0. Okay, so here now, suppose further now we will have different cases. What are those cases that just now, suppose our x is discrete. Suppose x, this random variable x is discrete random variable. Okay. And it is taking these values like x equal to, say, -3, -2, -1, 0 up to 4. Then how I will get this probability? Nothing but I will add probability x from x equal to -3 plus probability x equal to -2 plus probability x equal to -1, going on up to probability x equal to 4. Okay, so if x is discrete. Okay, yeah, furthermore, if I say that my probability x is x, this I give some symbol, say g at x. Okay, so what will be this value? This value, it will be g at -3. This value, it will be nothing but g at -2. And similarly, this value, it will be g at -1. And this is g at 4. So basically, if our x is discrete, what will be this probability? Nothing but summation of gx. Okay, so summation of gx x from -3 to 4, or summation probability x takes the value x and x from -3 to 4. Okay, and obviously, suppose if this is the case, okay, and our x is discrete random variable, and it is again taking the values like 0, 1, 2, 3 up to 7, then this will be this value, it will be nothing but summation that probability x takes the value x, but x is starting from 0 up to 7. Now, suppose our x is continuous. This random variable is continuous. In that case, how I will calculate this probability? It will be nothing but integration of some special function fx between -3 to 4. And what will be this some special function? It will be nothing but our probability density function. Okay, so that's how we define the CDF. And similarly, in this case, suppose our random variable is continuous. So this probability, it is nothing but integration from 0 to 7 of fx dx, where what is this fx? Our probability density function. Actually, this meaning of cumulative, it is the same meaning that is in CGPA, the cumulative grade point appraisal. One thing is TGPA, the term grade point appraisal. Another thing is cumulative. Actually, whatever GPA is there, whatever grade point appraisal, it is there. The formula is summation CIGI I1 to N. I1 to N divided by summation Ci again I1 to N. So whatever GPA, whether it is CGPA, cumulative grade point appraisal, or term means semester grade point appraisal, the formula is same. The formula is same. Where what is CI? CI, it is the total credit. It is the total credit of the ith course. And what is GI? GI is the grade obtained by the student in the ith course. Okay. Now these grades further they are converted into numbers. So every institute has some numbers corresponding to every grade. Okay. For example, say in some institute it is possible that A plus grade it has corresponding number 10 or 9 or whatever. So these grades are converted into the numbers, okay, and then this formula is applied to calculate the TGPA or CGPA. Now, if it is TGPA, what will be this N? This N, it will be the number of subjects which the student has studied in that term only. For example, suppose if I am calculating TGPA for fifth semester, I am calculating TGPA for fifth semester for a certain student. What will be N? N will be number of subjects studied by the student in the fifth semester only. But if I am calculating CGPA up to fifth semester, if I am calculating cumulative grade point appraisal for the same student up to fifth semester, then what will be this N? Once again, this N, it will be total number of subjects, okay, studied by the student up to fifth semester. Means in that case, this N, it will start from our first semester. Okay, so means starting from the first semester, whatever his first semester. Okay, because for lateral entry students in some institutes, the first semester actually starts from the second year or third sem. Okay, so in case of CGPA, this N, it will be total number of subjects studied by the students starting from the first semester up to the present semester. Okay. So the word cumulative, what is the meaning of word cumulative? Okay, it is it here the meaning that it is start from the starting and come up to the present. Okay. Actually, there is another meaning of cumulative also that we will not use here. Another meaning of cumulative also that start from the end. Start from the end and come to the present. There is another meaning of cumulative, but that meaning we are not using here. So now you can see this is the basic definition of our CDF, the value of CDF at X. Probability that X takes all values up to X, obviously start from starting. Okay. So now here obviously what must be the case that our random variable must be discrete, and what must be the case that our random variable is must be continuous. Okay, so this I have already discussed. So here what is the present X? X is X, here X is present X. Okay, so even here what is the top limit? You can see the top limit is X. Even here what is the top limit? What will be the top limit of the variable? It is X. And here the symbols used are T. The symbol uses T. And when I explained, I use the symbol X. But whether we use the symbol X, T, Y, means I can write that this probability that X, it is less than equal to X. This I may write that it is whatever the lower limit up to the present X. I may write Fy dy also. Okay. So these are merely some symbols, and they will not change the meaning of the function. Now here, fx, this CDF, it is integration. It is integration of PDF. This fx, this is our CDF, and this small f, it is our PDF. So please mind, there are two types of functions by now. One is CDF, and for the CDF, the usual symbol, it is capital F. For the CDF, the usual, not always, it is capital F, and there is another function which is small f, it is PDF. So CDF, it is the integration of PDF. So what must be PDF? It must be differentiation of CDF. Actually, we know that in a certain sense, differentiation and integration, they are reverse processes. So if fx, you can see this fx, it is integration of CDF. It is integration of CDF. Oh, sorry, PDF. The CDF, it is integration of PDF. So PDF, it must be differentiation of CDF provided this derivative exists. Okay. So here I am telling you this result, telling you about this result in a rough mathematical sense, but the exact proof of this result, it is based upon a very famous result in mathematics, that is what we call the fundamental theorem of integral calculus. So the proper proof of this result I am not discussing, but what is the crux of that theorem, the theorem, fundamental theorem of integral calculus? The crux means what we can say, the overall meaning of that theorem is it is that differentiation and integration, they are reverse processes in some certain sense. Okay. So now, in order to understand this result, basically suppose we have our real number line. So here it is the starting point minus infinity. Okay, and here it is a, and here it is b. Okay, actually the starting point, it may be any real number. It may be -3, -2, 0, 10, whatever the starting point. So to cover up all the cases, what we do, we take it as minus infinity. And what I need here, I need this probability that x is in this range, probability that x is in this range. For that, what I will do, first of all, I will calculate this whole probability. I will calculate this whole probability, start from the starting. And this is nothing but probability that x is less than equal to b. Okay. This I may write, this is nothing but probability that minus infinity x less than b. And this is nothing but f at b, the value of CDF at b. Then I will calculate this much probability, means up to A. I will calculate this much probability, which is up to A. So this is nothing but probability that x takes all values up to A. Obviously, this is f at A. Okay. Now, if I subtract, you can very well see, one can see here that if I subtract, means FB minus FA, means up to this total probability minus this probability, what I will be having, it will be nothing but this probability, which is nothing but this. So this explain this result. And I told you that PDF, it is nothing but the differentiation of CDF. So this is one of the important results for us. Actually, we will use this particularly whenever CDF is given for any random variable. CDF is given, but we need PDF. Okay, the probability density function. Then we will use this formula, and this formula, this is the way, this formula is the way of obtaining PDF from CDF. This formula, it is the way of obtaining PDF from CDF in case of continuous random variable. In case of continuous random variable, in case of a discrete random variable, how we obtain PDF from CDF? Okay, it is in a certain different way. Actually, we can talk about differentiation and integration. We can talk about differentiation or integration if our function is continuous. In case of discrete function, our differentiation integration, these concepts, they don't exist. Rather, there are some parallel results. Okay. Actually, they are in terms of differences. Okay. That I will discuss in some another example. So here we have a car agency that sells 50% of its inventory. Inventory means whatever is in the stock to run the business. So 50% of it inventory of a certain foreign car, which are equipped with side airbags. Okay, means 50% of the cars which are to be sold by the agency, they are with side airbag. And what about the remaining 50% of the cars? So the remaining 50% of the cars, they will be without side airbag. Okay. So here, for any car to be sold by the agency, for any car to be sold by the agency, there are only two options available. Okay, what are those? That either it will be with the side airbag or it will be without side airbag. Okay, and both type of cars, they have equal chances. They have equal chances of being sold. Equal chances of being sold. How? Because 50% of the cars, they are with side airbag, and the remaining 50% are without side airbag. Actually, this concept, it is somewhat with the actual scenario. Within India, most of the means not so sedan cars, luxury cars. Actually, the luxury cars like Mercedes, they come with side airbags. Otherwise, the cars which do not come in the luxury class, they have only front side airbag. Okay, although these days, the companies are trying to equip the cars with side airbags also. Okay, so this is just actually taken from the same scenario. So find the formula for probability distribution of the number of cars with side airbags among the next four cars to be sold by the agency. So again, what we need probability distribution of some certain number of things. We have to find probability distribution of some certain number of things. Now, these certain number of things, they must be our random variable. So here, what is my random variable x? It denotes the number of cars with side airbag, with this side airbag. Okay, so it is the number, so the random variable x, it denotes the number of cars with side airbags the among the next four cars to be sold by the agency. Okay. So now this X, what values it can have? Actually, this can have value either 0 or 1 or 2 or 3 and at max 4. Means out of these four cars, next four cars to be sold by the agency, there is zero car with side airbag, or there is one car with side airbag, or two car, or three, or at max four. And if out of these four cars, to be sold by the agency, if there is say one car with side airbag, what about the remaining three? They will be without side airbag. If there are two cars with side airbag among these four cars, okay, then what about the remaining two? The remaining two will be without side airbag. And now what we need probability x is x. Yeah, the usual symbol is fx. Now this fx, okay, or this probability x is x. So this fx, actually it is given by 4cx divided by 2 raised to power 4. Where what is this x? It can be 0, 1, 2, 3, 4. So this fx, it is given by this formula. How this formula? For that, actually, for the first car, for the first car to be sold by the agency, to be sold by the agency, how many options are available? There are two options available. What two options available? Either this car, either it will be with side airbag or without side airbag. Similarly, for the second car to be sold by the agency, how many options? Again, two options. Similarly, for the third car, okay, to be sold by the agency, how many options are available? Two. And what about the fourth car? So the fourth car to be sold by the agency, how many options? Once again, so for these four cars to be sold by the agency, for these next four cars to be sold by the agency, total how many options or how many outcomes are available? It is 2 into 2 into 2, 4 times, that is 2 raised to power 4, which is our total or exhaustive number of outcomes or options available. Now, how to calculate these favorable number of cases? Actually, for favorable number of cases, suppose I have got these four cars, C1, C2, C3, C4, which are without side airbag. I got my these. These are the four cars which are which are with side airbag, which are with side airbag. Okay, so I got my four cars which are with side airbag. Now, out of these four cars, in how many ways I can select zero car? Out of these four cars with side airbag. Okay, in how many ways I can select zero car? That is nothing but 4C0. Out of these four cars, in how many ways I can select one car with side airbag? That is 4C1. Okay, similarly, for two cars, it will be 4C2 and going on. Okay. And moreover, about these combinations, I have discussed in very detail in our very first lecture on random variable. Okay. So if someone is interested, he or she may watch that lecture. So here we have, this is the formula, means this is the formula for our probability mass function. Okay. So one by one, we can substitute that it will be 4C0 divided by 16. It will be 4C1 divided by 16, 4C2 divided by 16, going on. Okay. What is this 16? It is nothing but 2 raised to power 4. Question we have, also find the CDF, cumulative distribution of this random variable X. Also find the CDF. Okay. And now, what will be if I denote by F? So what is the value of F at X? It is nothing but probability that X takes all values up to X. Obviously start from starting. And here X is starting its values from where? From 0. So by chance, suppose I need the value of F at 3. I need the value of F at this value of random variable, which is 3. So it will be nothing but probability that X takes all values up to 3. Start from the starting 0. Similarly, if I need the value of F at 2, that will be probability that X takes all values up to 2. Okay, so that's how we will define our CDF. And for that, I am directly taking you to the values. Here are those values. One can very well see. So here, what is this? F at 2. Actually, this F at 2, it is nothing but probability that X takes all values up to 2, which is nothing but probability that start from 0 up to 2. So this is nothing but probability that X is 0 plus probability X is 1 plus probability X is 2. Okay. And what is this value? It is actually, this is F at 0. And what is this value? Actually, this value, it is nothing but 4C0 divided by 16. So basically 1 by 16. Okay, so you can see this actually this value. It is 1 by 16. And now what is this value? F at 1. It is nothing but this. X equal to 1, which is nothing but 4 by 16. And this value, it is nothing but this. Okay, which is sorry. Yeah, it is okay. And this value F at 2, it is nothing but 4C2. This value is 4C2 by 2 raised to power 4. Okay. And this is nothing but 6 by 16. 6 by 16 is nothing but 3 by 8. Okay. And you can see the values are actually given here, the values of the probability mass function. Okay. And please mind, what is this capital F? This capital F is CDF, the cumulative distribution function. And what is this small f? It is probability mass function, which is basically a probability distribution function. Okay, so that's how we will calculate the value of f at 2, f at 3, and f at 4. And obviously, what will be the final value of CDF or the value of the CDF at the final point? The value of the CDF at final point, it will be 1. Why? Because what is this thing? It is nothing but sum of the all the values, sum of all the values of the PDF start from the starting up to the total final value. Obviously, it will be 1. And see here, what is the value of f at 0? So the value of f at 0, it is nothing but probability that x takes all values up to 0. Now, below 0, is x taking any value? Means below 0 means is x taking any value? -1, -2, -3? No, it is not taking such values because here random variable is number of cars. So number of cars can't be -1, -2, it can't be negative. So here x, it is taking what minimum value? 0. X is taking minimum value 0. In other words, this x is not taking any value which is less than 0. This x is not taking any other value which is less than 0. So what will be this probability? It will be nothing but probability x is 0, which is nothing but f at 0. Okay. So further, this is 1 by 16. Okay. So here you can see this is also fx. Actually, there are two ways of writing or representing or expressing. There are two ways of writing, representing or expressing the CDF. So here this is one more way. Okay, so I repeat, one way I have already discussed. So this is the one way of writing, representing, or expressing the CDF. And this one, whatever you are seeing here, this is another way of writing, representing, or expressing the CDF. Actually, this way, this way of writing the CDF, actually, it is more useful or helpful in the case if our random variable is continuous. I repeat that writing or expressing the CDF in this way, in this form, it is more useful, more meaningful, or more helpful if our random variable is continuous. Actually, this is my personal opinion. Someone may differ from my opinion. Actually, what I am saying, so actually, this way it may confuse a beginner. Means writing the CDF in this way, it may confuse a beginner. Okay. Why? Because here you can see the x is written in terms of some range. It is written in some range. Okay. For example, here x is in the range 1 to 2. Here x is in the range of 2 to 3 going on. And from here, someone may, means a beginner. A beginner may conclude that this x is continuous. From here, some beginner student, he or she may conclude that our x is continuous random variable. Why? Because I had discussed that if the values of a random variable they lie in some range, in some continuous scale, in some interval, then our random variable is continuous. Okay. So that's why I have mentioned that this way it may confuse a beginner. Actually, although the values of x they are given in some range, but still x is discrete. Why? If I ask that in this range between 1 to 2, between 1 to, so if I ask that in this range between 1 to 2, what is the maximum value which x can take? What is the maximum value which x can take? Then that value is 1. Why? Because what is our x? It is number of cars. Okay. So number of cars, it can't be 1.99999, which are closer to 2. Okay. Although 2 can't be there. Okay. So in this range, what is the maximum value which x can take? It is 1. And so what's the meaning? In this range, what we are looking for? We are looking for f at 1. And what is the value of f at 1? It is 5 by 16. Now, in this range, what is the maximum value with which this x can take? That is 3. Okay. So once again, x can't be 3.99999 going on because x is, once again, x is number of cars. So in this range, what is the maximum value which x can take? It is 3. So basically in this range, what we are looking for, we are looking for value of f at 3. Similarly, in this range, what is the maximum value which x can take? That value is 4. Okay, because 5, 6, any other value, this x is not assuming. So in this range, what we are looking for? We are looking for f at 4. And what is the value of f at 4? It is 1. Okay, so that's how to explain this way of writing or representing the CDF. So the remaining part of this question was that we have to verify. Okay. So we have to verify using CDF. Please read the question statement again, that using the FX, capital FX, the CDF, we have to verify that f at 2, it is nothing but 3 by 8. Actually, we already know that this f at 2, the value of PDF at 2, it is 3 by 8. Why? Because this f at 2, it is nothing but 4C2 divided by 2 raised to power 4. Okay, by the formula for our PDF or the probability PMF, the probability mass function. So value of f at 2, it is nothing but this. So this is actually 6 by 16, which is further 3 by 8. So we already know the value of this F2, it is 3 by 8, but now we have to verify this thing. Okay, verify that F at 2 is 3 by 8, and moreover, we have to verify using CDF. Using CDF. For that, if you look here, you subtract f at 1 from f at 2. We subtract f at 1 from f at 2. So here we will have f at 2 minus f at 1. Okay. So this will be, this cancels, this cancels. So what will be remaining? This will be f at 2. So this will be what? 11 by 16. Okay. Minus 5 by 16. And that will be nothing but 6 by 16. So 3 by 8. Okay, so that's how we have verified that f at 2, it is 3 by 8, but using what? Using CDF. Similarly, f at 3 minus f at 2, that will be nothing but f at 3. Okay, so it may go on that the value of f at 4. Okay, please mind this f at 4, the PDF, it will be nothing but f4 minus f3. Okay, and now this is the way. So this is this one, whether this one or this one. These are the ways of obtaining PDF. These are the ways of obtaining PDF from CDF. These are the ways of obtaining PDF from CDF in case of discrete random variable. Okay. In case of a continuous random variable, how we obtain PDF from CDF? How we obtain PDF from CDF? That is nothing but simply by differentiating the CDF. But here, obviously, our random variable is discrete. We can't talk about differentiation or integration. So here, how I will obtain the value of PDF at any particular point? It is nothing but the value of CDF at that point minus the value of CDF at the previous point. I repeat, how I will obtain the value of PDF at any particular value. At any particular value, it is nothing but the value of CDF at that particular value minus the value of CDF at the just previous value. Okay, so this is how we obtain PDF from CDF from the how we obtain PDF from CDF if our random variable is discrete. Okay, so this one, it is the basic of MCQs which are asked in various competitive exams. Okay, so thank you everyone.